Hi, everyone. So we're continuing with our exploration of the proof of Fermat's last theorem. Last time we just went through the first couple pages of Wiles' proof and discovered all the things that we don't understand. So the first thing he mentions, of course, is elliptical curves. So we're going to, I think, start with trying to understand a little better what elliptical curves are. Now, I assume this is a big topic. So for this video, I have several books on elliptical curves. So I just want to go through several of them and pick one that we think might help us out the most. Then we'll go through it. And then I think we're going to have to brush up on some abstract algebra before we keep going. So, and then also before we start doing that, I actually know I've watched some videos, so I have a sense of basically what elliptical curves are, but how they relate to Fermat's last theorem is another question. So, at some point, I think I'll take a first pass at like a one sentence explanation of what I think Fermat's last theorem is about. But for now, let's just pick an elliptical curve book. So this first one is by William Fulton, and it's an introduction to algebraic geometry. That's really what we're talking about here. And the book is called Algebraic Curves, but that means elliptical curves. So he has his prefaces here. Let's look at the table of contents. Here's the word affine. I have no idea what the word affine means, but I think it's good that I know that Wiles talks about affine a lot, so at least we're on some kind of we're on the right track here. We might learn more than just elliptical curves by looking at this stuff. So there's some algebraic preliminaries, affine space and algebraic sets, the ideal, and then again, stuff that I don't know what it is. Hilbert basis, irreducible components. I'm just looking to see if any of these are things that that Wiles mentioned. So this looks good. Actually, we need to look a little bit at the preface to see what's going on. So this text has been out of print for several years with the author holding copyrights. Without charge. Okay, that doesn't say anything. When this book first appeared, there were few texts available to a novice in modern algebraic geometry. Since then, many introductory treatises have appeared. There's been a good deal of growth. Algebraic geometry is highly developed and thriving field of mathematics. It is notoriously difficult for the beginner to make his way into the subject. That's interesting. There are several texts on an undergraduate level that give an excellent treatment of the classical theory of plane curves, but these do not prepare the student adequately for modern algebraic geometry. On the other hand, most books with a modern approach demand considerable background in algebra and topology, often the equivalent of a year or more of graduate study. The aim of these notes is to develop the theory of algebraic curves from the viewpoint of modern algebraic geometry, but without excessive prerequisites. That sounds like exactly what we want. So that's pretty good. It's interesting that this book was first written in 1969, so fully 25 years before Wiles did his, before anyone did any of these proofs, before the connection with Taniyama Shimura and what led to Wiles' proof. I don't think any of that's been done yet when this book was first written. So that's interesting. Okay, that one sounds like a good one. Let's look at a few more. The next one is Joe Harris, Algebraic Geometry. These are these good books, these yellow books that I like. I'm sure everyone does. So this book was based on a one-semester course given at Harvard in 1984 It's intended to be a first introduction to the subject. Even so, algebraic geometry has developed tremendously over the last century. It used to be practiced in a relatively concrete, down-to-earth level. The main objects of study were projective varieties, and the techniques, for the most part, were grounded in geometric constructions. This approach flourished during the middle of the century and reached culmination in the work of the Italian school around into the 19th century. Ultimately, the subject was pushed beyond the limits of its foundations. By the end of the period, the Italian school had progressed to the point where the language and the techniques of the subject could no longer serve to express and carry out the ideas of its best practitioners. That's interesting. This was more amply remedied in the course of several developments beginning early in this century. So there's Zariski, the abstract algebraists. Weil introduced the notion of abstract algebraic variety. I think Weil's name is in the Taniyama-Shimura conjecture as well. In effect, redefining the basic objects studied in the subject. I think this is what Fulton was talking about with the old way versus the modern approach, that the modern approach is more difficult. Then in the 50s came Sear's work, introducing the fundamental tool of sheaf theory. Finally, in the 60s, Grothendieck, Artin, Mumford, and others introduced the concept of a scheme. I think we've definitely heard of sheaves before. I don't remember if we've heard of schemes. This, more than anything else, transformed the subject, putting it on radical new footing, which is what led to Fermat's last theorem. So what's the best way to go about learning the subject? If the goal is simply to see what algebraic geometry is about, to get a sense of the basic objects considered, the questions asked about them, and the sort of answers one can obtain, you might not want to start out with the more technical aspect of the subject. On the other hand, if your ultimate goal is to work in the field of algebraic geometry, it might seem that the best thing to do is to introduce the modern approach early on and develop the whole subject in these terms. That's a tough question. I kind of think it would be good to at least get a little bit of just an introduction to it. Even in this case, though, you might be better motivated to learn the language of schemes and better able to approach the insights offered by it if you had some acquaintance with elementary algebraic geometry. That's what I think. So classical algebraic geometry is a simply glorious subject, one which is beautifully intricate and has a tremendous wealth of examples. So this also sounds like a good book. But this is a graduate text. The other one started as an undergraduate text. I think that one might be better, but this is definitely a good one too. Next, another graduate text. Again, an introduction to algebraic geometry, using the methods of schemes and cohomology. That's another thing we saw in Wiles' proof. The main subject are algebraic varieties in an affine or projective space over an algebraically closed field. These are introduced in chapter 1. Then the methods of schemes and cohomology are developed in 2 and 3. The last chapters, 4 and 5, use these methods to study topics in the classical theory of algebraic curves and surfaces. The prerequisite for this approach are results from commutative algebra, which are stated as needed in some elementary topology. No complex analysis or differential geometry is necessary. I have actually taken a class in differential geometry. In fact, I don't really understand what algebraic geometry is, because differential geometry makes sense to me because everything is smooth. So that's an interesting question that we have to figure out. The basic graduate course, following a basic graduate course in algebra. Okay, this one is more advanced already because it requires graduate algebra in order to even get into it. So here's the schemes, cohomology, curves, surfaces, then appendixes, and then the Weil conjectures. So this one seems tougher. But Okay, I think this one's a little tougher. We didn't look at the, this is the other one. Let's look at the table of contents here. So this is interesting. This is very different from the first book, isn't it? But I'm not sure. This seems like a real introduction to the whole topic, I think. So, okay, well, we'll see. So we have another one by the same guy. This is an undergraduate text. That's good. Oh, by the way, look at this. Here's Ken Ribbett. He's been an editor of this series for a while, and remember, he's the one that proved the connection between Taniyama Shimura and Fermat's last theorem. I've not found anything in Lobachevsky's work that's new to me, but the development is made in a different way from the way I had started, and to be sure, masterfully done. Okay, whatever. In recent years, I've been teaching a junior senior level course on classical geometries. This book has grown out of that teaching experience. I assume only high school geometry and some abstract algebra. The course begins with a critical examination of Euclid's elements. Okay, this would be fantastic, but I think it might be starting too far away from where we want to be. We might decide to take another step back and start here, because this definitely introduces us to the field, but it's really all Euclidean. Let's skip that one. Here's just elliptic curves. Graduate text. I have to say, given that the undergrad book, that first one we looked at, seems to be pretty good, I don't think we should start with a graduate text. I think we should start at least with the undergrad text, at least till we get a sense of what's going on, because I don't think that is going to be easy. Being an amateur in the field of elliptic curves, I would never have completed a project like this. Okay. Rational points on plane curves, elementary properties, factorial rings. Okay. That one seems okay, but now look, this is interesting. This is Sir himself, and Sir is one of the ones who was instrumental in the whole advancement of this field. So this is definitely an interesting book. This is from 1973. Uh-oh, what happened to I think my computer just died. Okay. So this is definitely cool. The first one's purely algebraic. It's divided in two parts. Its objective is the classification of quadratic forms over the field of rational numbers. It's achieved in chapter 4. The first 3 chapters contain some preliminaries. P-adic fields, there's something we need to learn about. Integral quadratic forms, analytic methods, holomorphic functions, theorem of Dirichlet. Wiles mentioned Dirichlet. Oh, and then chapter 7 deals with modular forms, and in particular theta functions. So this is very interesting, but I think too much for us right now. This is what we want, but I think it's too much. So, boy, let's skip this one and think about coming back to it. Okay, we just have 2 more books to get through. This is another graduate text by Joseph Silverman, The Arithmetic of Elliptic Curves. There's an actual elliptic curve, so that's a good sign. There's Ken Ribbett again. So 14 illustrations, that doesn't sound like very many. Let's look at his first edition. Preface to a textbook frequently contains the author's justification for offering another book. Yes, of course it does. For a chosen topic, there's little need for such an apologia. Well, I don't know. Considering the vast amount of research currently being done in this area, the paucity of introductory texts is somewhat surprising. So this is good. It's an introductory text, but it's a graduate level text, so I think that it might still be over our heads. Parts of the theory are contained in various books of Lang. I'll have to tell you guys sometime about my interactions with Serge Lang, especially 135 and 140. Thus, the author hopes that this volume fills a real need both in the serious student who wishes to learn the basic facts of the arithmetic of elliptic curves and for the research mathematician who needs a reference source for some basic facts. Okay, this sounds like a good book. The small price paid for learning a bit of algebraic geometry is amply repaid in a unity of exposition that seems to be lacking when one makes extensive use. Okay, well, he's certainly wordy. The last point is worth amplifying. Okay. So let's look at the table of contents. Affine varieties, projective, maps between varieties, algebraic curves, geometry of formal group, and so on. Let's see how it starts. Oh, I've heard this word before. Diophantine equations. Fermat's last theorem, the Pythagorean equations are diophantine, but I don't know why. The solution to polynomial equations of integers or rational numbers. So he's just getting in here. This is actually very close to why elliptic curves are important to Fermat's last theorem, because what they do is they transform a squared plus b squared equals c squared into one of these elliptical equations, and that opens up all of the study of elliptical equations to this topic. So I'm gonna show that in more detail in a couple of lectures. But again, this one looks like another okay book, but I think we need to stick probably with that with the that undergraduate one. I just think that'll be an easier one. But let's look at the last one. Last one is Skorobogatov. This one doesn't have an intro. The basics of commutative algebra, Noetherian rings, affine geometry, smooth and singular points. So there's Serge Lang again. If we really want to get into it, we could go through his whole book. That would take us a couple years on its own. Lekebia field. Okay. Well, this one's good, but I think, as you can tell, I think I've kind of already decided. I think we'll start with Fulton because he says that it's an undergrad text and it's a good place to start. Okay, so that's it. Let me just tell you quickly what we're going to go over next. So I think the first thing I'm going to do before we start on this book is do just a very basic Wikipedia level overview of elliptic curves, just to get a very basic sense of what they are. Then I'm going to do the first real math video. I'm going to explain how we get from Fermat's last theorem to elliptic curves. So that will be the actual math of it. Just requires manipulating, and then you can turn a squared plus b squared equals c squared into an elliptic curve. So that'll be actual math. Then the next one, I'm going to do my most basic understanding of what Wiles' proof is. That is, what's the connection between Taniyama Shimura and Fermat's last theorem. How does the one prove the other? So let me write that down. Basic level. How does Taniyama, Shimura imply FLT. Then next we'll start on Fulton's book. And I think that is going to require then immediately some more abstract algebra. So I think before we even start on Fulton's book, the first 2 pages of Fulton's book are about the basics of abstract algebra that we'll need in order to understand the book. So we're going to have to go over that in some detail. So then a refresher on abstract algebra basics. And then hopefully we'll start very shortly actually learning something about elliptic curves and go from there. All right, thank you. Don't forget to subscribe and go to Patreon and sign up on Patreon and all that good stuff, okay? Thank you. Bye.